Daily peaking inflates prompt AB false wins unless an SPRT controls when the experiment stops. You'll apply a Bernoulli SPRT with explicit error bounds that updates per evaluation and reports outcome and evidence, stopping only at boundaries. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. You launch 2 prompts for the same support task. Prompt A is the current version. Prompt B is a rewrite that seems clearer. Each response gets a pass or fail label from an evaluator. After a few results, B may look ahead. That is tempting, but stopping right there can ship a lucky streak instead of a genuinely better prompt. A normal A/B test usually chooses a sample size before it starts. Sequential testing lets you check results as they arrive. The important part is not checking less often. It is using rules that account for frequent checking, so your decision stays trustworthy. We will build a small test that reads evaluator outcomes one at a time, measures evidence for B, and stops only when that evidence is strong enough. A Bernoulli result simply means each evaluation has 2 possible outcomes here: pass or fail. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We first need a simple view of the early results before deciding whether they mean anything. This snippet turns 2 prompt result streams into simple pass rates. The daily dashboard temptation starts here. Prompt B looks better on this tiny slice, but the slice is not yet a stopping rule. Wins A and wins B stand in for evaluator pass or fail labels from prompt responses, so 1 means the answer passed, and 0 means it did not. The code only counts successes and divides by total evaluations, giving a quick but incomplete read. The visible output shows the raw rates, which is useful context before adding valid sequential boundaries. A higher rate is encouraging, but it does not tell us whether we have seen enough evidence to make a safe release decision. Raw rates show the direction, but now the test needs clear limits for wrong decisions. This example replaces repeated informal peaking with explicit error limits. Alpha is the false positive bound for shipping B when the null rate P0 is true, and beta is the false negative bound for missing the target rate P1. The code converts those limits into log likelihood decision boundaries, high and low, for a simple Bernoulli SPRT. Raising alpha or beta makes the boundaries easier to cross, while lowering them demands more evidence before stopping. The visible output shows the 2 thresholds that every later check must respect. These settings force the team to state how much risk it accepts before the results arrive. The boundaries are ready, so the next need is to update evidence from every new B evaluation. This code scores the actual B outcomes against the 2 hypotheses, instead of rereading a p-value every day. Each pass adds evidence toward P1, while each failure adds evidence toward P0, and the loop stops only if LLR crosses high or low. The decision variable stays at keep testing when the stream has not crossed either boundary. That is the key behavior engineers want during prompt experiments. Look as often as the process allows, but only act on boundary crossings. The visible output shows that the early-looking B rate is not yet decisive. The test is not ignoring the early gain. It is refusing to confuse a promising signal with a finished decision. For more practical lessons on AI engineering and data workflows, you can subscribe and keep building these skills. An undecided result is useful, but we also need to see how the test saves work once evidence keeps arriving. This snippet shows the other side of the trade-off. Fixed sample sizes can keep spending calls after the evidence is already enough. More B extends the same result stream, and enumerate records the exact evaluation where the boundary is first crossed. Once LLR reaches either boundary, Stop N captures the stopping point, and saved counts the evaluations not needed from the planned batch. This does not make the test more aggressive. It uses the same high and low from the declared error bounds. The visible output shows both the stop point and the calls avoided. That matters when evaluator calls are slow, costly, or reviewed by humans. The logic works for one stream, so the final step is packaging it into a repeatable experiment helper. This example turns the pieces into a small baseline you can reuse across prompt runs. Run SPRT owns the sequential update, the two boundary checks, and the fallback inconclusive result if the stream ends first. After the function returns, logrow is the compact tracking record you would save beside prompt IDs, model settings, and evaluator versions. Keeping the stopping logic in one function also reduces the chance that different experiments apply slightly different rules. The visible output shows the selected outcome, how many evaluations were used, and the final evidence score. That record makes later comparisons easier to audit, instead of relying on a dashboard screenshot. When evaluator labels are noisy, monitor the evaluator itself as carefully as the prompts. A sequential test can control its stated error rates, but it cannot rescue pass or fail labels that do not match real user quality. Use a stable rubric, keep the task mix consistent, and rerun important wins on a fresh holdout set before a broad rollout. This example shows why early prompt gains should trigger measurement, not immediate celebration. The SPRT lets you inspect every result while keeping a disciplined stopping rule, and it can stop early when the evidence becomes strong. Try changing alpha or beta, and notice how the boundaries become easier or harder to cross. Then compare how many evaluations the same outcome stream needs under those different risk limits. What practical AI evaluation topic would you like to explore next? Share it in the comments, and subscribe for more clear Python lessons on building reliable LLM systems.